Schur goes on and answers the question, oranges and elephants don't mix. Let's say we have a matrix representation, and now, I'm not a fan of this notation, but okay. So because this was invented by Germans, these matrices are denoted D, abbreviation for Darstellung. Stellung means, arrangement or place. So I put it there. That's the representation, Darstellung. So you see these all the time. And there could be representation 1. For example, two-dimensional matrices that rotate circled by angles in the plane. And it has a property that every group element has a matrix of that dimension, and it belongs to reducible space, meaning that as I apply these matrices, I fill out the space and I don't run out of it. So it's some representation 1 space, and the number of group elements, abstract group elements, is H. Abstract means they satisfy the multiplication table. Brackets means that I'm using some matrix representation, D by D square matrix, which represents this. So that's representation 1, and assume we have 2 of them, and we don't know whether the same one or different or whatever. But they always have the same number of elements because that's the number of elements in the group. And they have a property that I multiply them, I reproduce correctly multiplication table. Assume there are 2 irreducible representations, these smallest atoms. You can have all kinds of different matrix representation, but if I multiply group elements, representation of group element 1 and 2, then what comes out is representation of the element, which is a product of these 2 elements in the abstract multiplication table. So for example, if A1 is a flip, then doing it twice, I get identity. So as long as the representation of flip is such that when I square that matrix, I get 1, I have a representation. Their matrices have dimensionality. So they have dimensions L1 and L2. Then I can imagine that there was a matrix which was a rectangular matrix. So I can imagine that if I multiply di, I take a rectangular matrix, which is of the L2 size. And when I multiply it from the other side, I also get the correct size. So assume it exists. Then either m equals 0. So that matrix is impossible. I can't convert these guys into each other. Or D1 is a similarity transformation of D2. Now, whenever 2 representations are similarity transformation, they're morally the same representation. It just says in one coordinates, I write it as D1s. But if I rotate the coordinates, it'll be D2. And of course, they're all the stupid notations. This is true for every group element. This statement says I cannot have different dimensions of representation, no oranges and elephants mixing up socially or otherwise. There is no M that will do that. So then I'm reduced to the situation that the dimensions are the same. So these are just square matrices. And then it says that if I have a square matrix that dealing with these 2 representations somehow relates them, but in my mind they're different, they cannot be different other than a little coordinate rotation, just relabeling of the axis or something. So that's part 2 lemma. let's prove it. What happens if dimensions are different? So let's say that L1 is either smaller or equal to L2. And then, as always, we look at our defining relation. This is our assumption. And then we manipulate it by taking Hermitian conjugate, as we have done all along. So then I get, when I Hermitian conjugate this, I get the matrix 1 on the left-hand side, AX Hermitian conjugate, and M becomes Hermitian conjugate. This guy, M, ends up on the left-hand side. This becomes D2 of AX Hermitian conjugate. Nothing. We have already proven that we can always choose a representation to be unitary. So let's assume that a unitary, unitarity means that U Hermitian conjugate is same as the inverse of the matrix, right? But if I take inverse of a matrix, that's the same as taking the inverse group element. That follows from requiring the multiplication table is respected.
By the Darstellung, we are referring to the representation of the group AX, or is it something different?
AX is a group element, so it's a representation. And we're assuming that we're looking at irreducible representations.
So D1 is one of the irreducible representations of AX.
And D2 is another,
okay.
Or maybe the same. In general, they're different.
Okay.
And this is now supposed to be true for every group element. So this is supposed to be true for a bunch of matrices, not just one matrix. So that means that this is the same as writing inverse of this group element, M Hermitian conjugate, inverse of the group element, representation of inverse in the other Darstellung. We multiply by M on the left, M, D times M, M Hermitian conjugate, D, to this same group element, the inverse one. And then, multiply it from the right. You get a hang of it from left. When I do it from the other side, I get equals, if I multiply the whole thing from this side, I get M plus, not plus Hermitian conjugate. So multiplying the original thing from the other side, D2, this guy, I'm sorry, D1, and it's obviously the same elements, I'll forget that. M Hermitian times M. So this part is obvious, but if I multiply from the other side, I had this relation which says I can replace M times D1 times D2, M on the other side. And out of all this MM that's showing up here and there commutes OAX, because we can choose A to be anything and inverse will be some other group element. So that means that this combination that we assumed before, M plus, by Schur lemma number 1 must be proportional to unity. So if you look at the case where L equals dimensions are the same, that means that inverse of M equals M plus over C. But that means that M1 is a unitary transformation up to the rotation. And that means when I multiply this on the left-hand side by Hermitian conjugate, I get D1 is take this, multiply by the inverse, right, M star. We get representation 1 of a group element AX equals M minus 1 E2. This is a similarity transformation, just change your coordinates. So that proves half of this Schur lemma part 2, which says that if they're the same dimension, then one is a similarity transformation of the other. So it's the same representation. It has all same properties. Or M equals 0. I'll let you just finish the proof in the book yourself. Just a zero matrix. Now, this is the warm-up for the greatest thing of them all, which is called the Orthogonality Theorem, which we'll do next time. So you're getting the hang of the thing. The way this kind of group theory works is you just do small steps. All of them are trivial and make sense, called lemmas, etc. And what comes out is pretty amazing. So I'll just write it down and then I'll explain it next time. So if I have a matrix representation, which means something that has two indices of representation, let's call it alpha, of some group element, let's call it G. So this is abstract element and it has a matrix representation. Matrix has two indices and they're different representations. So I give them name, 1, 2, 3, 4, or alpha takes values, which are names of representation. So this is a label. And these are indices that run over dimension of the space of the representation. So you multiply this by another matrix on any dimension, because they're all irreducible representations of arbitrary dimension. Let's call it beta. So this has three different labels, but you take the representation of the inverse of this element and you average over the elements, which means you take G to be all elements in the group capital G. There are H of them, and average means you divide them by a number of elements. This whole mess with zillion different indices is zero whenever these representations are different irreducible representations. So they must be the same to give you a non-zero answer. And it turns out you have to divide it by dimension of representation A, alpha. And then these guys have to line up. These are Kronecker deltas. So this whole holy mess, there's lots of indices. It's almost always zero unless all these numbers line up just the right way. So that's pretty non-trivial, not obviously expected. And at this point, I say bye-bye. So that's it. Bye. See you on Thursday. I'm in Portland. I don't have time for it.